What you see written at the top left-hand corner of the screen is what you might often see in textbooks as the limit definition of the derivative. And I'm going to try to explain it so it seems a little bit less intimidating. So let's say we have a graph of a line over here, and this line, let's call it f of x. This is our function. So you would have probably learned that to find the slope, you can just do delta y over delta x is equal to your slope. But now we want to ask the question, what if I wanted to know the slope right here, for example, just at one exact point? How would we evaluate that? There would be no delta x. You're not traversing any distance on the x-axis, so how are we going to find the value of this exact point right here? And the way that we can do that, we can sort of mimic an infinitely small step across the x-axis, is using the concept of a limit. So let's kind of mark up our graph here. So let's say that this point right here, where we want to know the instantaneous rate of change or the derivative, this point is going to be x naught. This is our first x value. And let's say there's some hypothetical point over here. And let's call this value, or on the x-axis, x1. And as a result, on the y-axis right here, we could say, well, when we're at x1, the point on the y-axis is going to be y1. And when we're at x naught, the point on the y-axis is going to be y naught. And we want to say, well, this distance, this delta x, this change in our x value, we want this to be an infinitely small step. We want this value to approach 0. And how are we going to do that? Well, we're going to take the limit of our slope as delta x approaches 0, because we want this distance to be as small as we can physically get it to mimic sort of the non-existent step in x that we would have at one instantaneous point. So let's rewrite our expression for the slope. Let's rewrite this as the limit as delta x approaches 0 of delta y over delta x. So this is already looking a little bit better. We're saying, okay, we're taking an infinitely small step on x. There's no finite values to compute for this delta x in the denominator. And it's pretty close to what we would expect, or it is exactly what we would expect if we were to take the derivative at this one exact point. So now we can expand on this further. Well, what exactly is delta y? Well, delta y is just y1 minus y naught. It's a change in something, so it is final minus initial. So if we take that into consideration, we can take this expression that we have just written and we can actually rewrite this. We can say, well, this is the same as saying the limit as delta x approaches 0 of y1 minus y naught over delta x. And these two expressions we know are equivalent. So now where can we go from here? Well, our function is f of x. So if we were to plug x1 into f of x, what would happen? Well, f at x1 is going to equal y1. Our output right here, as we established at x1, is y1. And the same thing is going to happen with x naught. If we input x naught into our function, the output is going to be y naught. So now we can actually rewrite y1 and y naught in our expression over here. So let's do that. So now we can say, well, this expression is actually just equivalent to the limit as delta x approaches 0 of, well, we know that y1 is actually equal to f at x1. And we know that y naught is equal to f at x naught. And all of this is over delta x. Great, so this is looking a little bit more like our expression over here, but we're not quite done yet. So let's take a closer look at this part right here, f at x1. So f at x1 is what happens at this point right here on the graph. And so we can actually rewrite this. So we can say f at x1 is going to be equal to f at x naught plus delta x. Now, why is this true? What is this in here? Well, we can say x1 right here, this point on the x-axis, is the same as what would happen if we started here at x naught and we added this distance that we're traversing on the x-axis, which we have by the way, made infinitely small as a part of our limit expression. So we can say that x naught plus delta x is equivalent to x1. And therefore, f at x1 must be equivalent to f at x naught plus delta x. It's the same logic as, for example, if I were to draw a graph and I started at 1 and I ended up at 2. Well, the distance between these two is going to be 2 minus 1 equals 1. And it's correct to say that 1 plus this distance of 1 is going to equal 2. It's going to equal our final position on this graph. So that's basically the same logic that we've applied here. So now we can throw this back into our expression that we have been writing. We can throw this back into here and we can say, well, this is just equal to the limit as delta x approaches 0 of f at x1 is equal to, now we know f at x naught plus delta x minus f at x naught divided by delta x. And that is the same expression that we see up here for the limit definition of the derivative. And what you often see happen in textbooks is that they'll replace this delta x, they'll replace it with a variable like the letter h. And that's the way that I've written it up here, actually. And I find that it's a little bit more helpful to sort of look at the expression and say, okay, well, that h is actually representing a delta x. It's representing this infinitely small distance that we are traversing on the x-axis to get this change. And this is nothing more than sort of the way that we would compute the slope, as we always have done if we were to sort of traverse an infinitely small distance. And I think that that way of thinking about it helps me understand a little bit better and hopefully helps you understand a little bit better as well.